Okay, so for the last, I don't know, what have we been doing this for? A month, give or take? 3 weeks? We've been talking about redox chemistry, right? The idea that something is going to gain electrons. Gain of electrons is GR, so that's reduction. Something else is going to lose electrons. LEO oxidizes. Oxidizing means reducing agent. Reducing means oxidizing agent. All that terminology, right? Well, I think all that stuff is really clever and really, important. But this topic here, to me, is the one that revolutionized not just chemistry and physics, but has revolutionized our lives. The idea of if somebody is going to lose an electron, I'm just going to use my hands here, this guy's going to lose an electron, this guy's going to gain an electron. If they come into direct contact with each other, that's how the electron transfers. But somebody, and I've got a few scientists we'll talk about here, they come up with this really clever idea of rather than having this guy lose the electron directly to this one right here, have it run through a bit of a circuit before it gets over to here. Does that make sense? And in doing so, that electron creates what we now know as electricity. The movement and flow of an electric charge is electricity. Today, our topic, we're going to talk about batteries. And hopefully you'd agree with me. Batteries have revolutionized our world, right? I mean, you have a calculator in front of you that runs off of batteries. Your cell phone has some of the most incredible battery technology known to man these days, where it not only can last for like a whole day running all of the apps that your phone does, right? It recharges fairly quickly, so you don't even have to put in new batteries every day. I am constantly amazed at my MacBook Pro. That thing recharges in like half an hour. It blows my mind because, I mean, have you guys ever had to use rechargeable batteries where you used to like take the AA batteries and plug them into something and put them in the wall? Well, like, I think even those are obsolete. So, I mentioned before the idea of being able to put a battery in a pacemaker so that you can regulate someone's heartbeat. I mean, without batteries, those people would have, I don't know if their lifespans would be as long as they are. You know what I mean? So this is like the application section now of redox chem. Because otherwise redox chem really kind of just looks like every other chemistry sort of equation, right? It looks like a single replacement reaction. That's usually what it looks like. So let's talk about some of the key terms you need to know about batteries then. So I already mentioned electricity. If you don't know this definition already, when Benjamin Franklin supposedly discovers electricity because his kite gets hit by lightning, what he was really experiencing was the movement of charges. Okay? And I'm going to skip down to the third one there. If you've taken physics before, hopefully you recognize the term a coulomb. Okay? If not, you will learn about a coulomb more later. Basically, a coulomb is a lot of electrons. Rather than trying to count electrons one at a time, which is kind of ridiculous, we just clump them all together as a big group of them. You've actually already experienced this concept in chemistry. That's like a mole. A mole basically says rather than counting atoms one at a time, we count them 6.022 times 10 to the 23 at a time. In the same way that rather than counting donuts by the singles, we count donuts by the dozens. Well, when it comes to charges, we count them by the coulombs, which is just a lot of electrons. Does that make sense? So, charges, by the way, if you want to know the notation, charges can either be positive or negative. We're mostly focusing on negatives right now, though. Coulomb is the unit, so the unit is a C, and sometimes, this is really confusing, but sometimes we use the letter Q, which is dumb because Q was also the unit for heat a little while ago. So, we run out of letters. Okay. If you've been in my physics class, you might recognize this right here. An electron is 1.60 times 10 to the minus 19 coulombs. Do you guys recognize that from last year? Like, it's a really common thing you'll see on a data sheet in physics. For our purposes, I actually want to flip it around. Rather than saying that one electron is a very small portion of a coulomb, I want us to try to figure out how many electrons are in a coulomb. Anybody have any idea how I would calculate that? Sure. Basically, what I think you described is we need the reciprocal. Right? We need to go this to the power of minus 1. Okay. Let me see if I can phrase that a little better in case you didn't catch that. This means that one electron is equal to 1.60 times 10 to the minus 19 coulombs. And what I'm asking us to try to figure out is how many coulombs are there in one electron? No, I did that wrong, didn't I? No, I did that right. One electron is equal to 1.60 times 10 to the minus 19 coulombs. If you do take to the minus 1 and flip the fraction upside down, it'll say that 1 coulomb equals a blank number of electrons. Did I lose you guys on that, or did that actually make sense? Okay. Anybody have the ability to do the minus 1 part? What'd you get?
6.25 to the power, or times 10 to the power of 18.
Say that again. 6.25.
Yeah.
Okay. Times 10 to the power of 18. So, long story short, if we ever talk about a coulomb, just so that you can kind of picture it, a coulomb is that many electrons. That's it. Right. So, basically, rather than counting electrons one at a time, which is kind of a ridiculous idea, we just count them in groups of 10 to the power of 18. So, think of it like a mole, only it's of electrons. We can measure then how fast the electrons are moving. Fast is really not the right word, but it works in my mind. In physics, again, this is why I'm kind of doing the overlap, just because it does overlap. We should talk about it. In physics, the term for speed is velocity, and velocity is measured in meters per second. Basically, how far do you go per unit of time? Okay. Well, in electricity, we have kind of a similar concept. It's called current. Current basically says how many electrons move per unit of time. Does that make sense? In a way, current is kind of like how fast is the electricity flowing. Does that make sense? So the unit you might have heard before is called amps. That's how many electrons travel per second. If you had 1 amp, then there are this many electrons traveling past a point per second. If you have 2 amps, there are double this number of electrons traveling past a point per second. Does that make sense? So the higher the amperage, in a way, in my mind, I like to just think of it as how fast are the electrons moving. I should show you guys some notation. If we ever see a battery, sometimes we'll notate a battery like this right here. Usually it's like this is meant to be part of a circuit, this is meant to be part of a circuit, and you get a small line and a large line. The small line is intended to be the negative side of a battery, and I'll talk more about that notation in a bit. And the large line is meant to be the positive side of the battery. Does that work? Electrons. What would electrons want to be attracted to? The negative side or the positive side? The positive side, right? Because what do electrons do? Well, electrons would want to repel other electrons. So electrons would want to leave the negative side and go towards the positive side. And that's what this diagram right here shows. Right here, the electrons are going towards the positive side of the battery, and they are leaving the negative side of the battery. Make sense? Electrons are negative, therefore they're going to go away from other negatives and go towards positives. Okay. For you guys who took my physics course, though, you might recognize the term conventional current. I don't want to get too much into that, but historically, scientists didn't know what the heck they were doing, and they thought that electrons were actually going from positive to negative. And so sometimes it's confusing. If we talk about conventional current, it's actually the opposite of what actual electrons do. Yeah, the flow of protons. They used to think that protons move, not electrons. So again, I don't want to do like I don't want to teach you all of physics, but I do want to kind of talk about a little bit of the overlap here. So there is a formula that in physics we would have used. It's I equals Q over T. I is current, and current is equal to how many charges you have flowing per second. Again, it's kind of like a speed. Okay? So that's one type of unit that we're going to encounter in our course. We will do current in chemistry, by the way. We're also going to talk about voltage, and voltage is known as a change in energy. Sometimes we call it a potential difference. The units for this are typically joules per coulomb, basically how much energy you have per bunch of electrons, or we use the term volts. Okay. And this is a physics formula that maybe a few of you recognize from last year as well. We're not really going to do much with it this year, obviously, in chemistry. But long story short, this is what I was just describing. A battery, then, is the whole concept of taking electrons that want to go from here to here, and rather than going directly, run them through a loop. So over here is someone who's going to lose electrons. What sort of things lose electrons? Well, if you lose electrons, you oxidize. And if you oxidize, you're a reducing agent. Does that make sense? So this hand over here is a reducing agent. It's going to lose electrons to this hand over here. But rather than going directly, run it through a wire. Does that make sense? Which means that this guy over here is the negatively charged part of the battery, because the electrons are going to leave the negatives and be attracted to the positives. Does that logic make sense? So, sometimes there's some good analogies for the terms current and voltage. I like this one, so I use this particular one here. Imagine you've got a water tank sitting up top really, really high, but there's a hole in the water tank. Imagine the hole is this big. How fast is the water going to flow out of that hole? A little bit. Let's say the hole was this big. How fast is the water going to flow out of that hole? Faster. That's current. Current is basically like how fast is the flow rate. If it's flowing really fast, you've got a lot of current. If it's flowing not so fast, then it's not. Does that make sense? So that's current, speed, basically. If you like that analogy. The potential difference is not based on the size of the hole in the water tank, though. The potential difference is based on how high the water tank is above the ground. So if my water tank is right here above the ground, how far is the water going to fall? Well, I don't know, like 2 feet. Does that make sense? But if you've got like the Calgary Tower, there's a water tank up there, then how fast is the water going to fall? Sorry, then how far is the water going to fall? Well, then it's falling a further ways. Does that make sense? That is how much potential there is in the difference it's going to fall. So that's voltage. Voltage is really based on like your height, and your current is kind of based on the hole in your tank. So this slide just kind of talks about what I mentioned there. This is actually right out of your physics notes from last year, by the way, or next year, I guess. I think I'll leave it. I've covered my point here. I found this cartoon, though, that maybe kind of makes sense. Amperage basically is how thick is the tube you're trying to go through. If the hole is really big, then you can fit a lot of current through it. Does that make sense? So voltage, though, is what's pushing it. Why is the water falling out of the water tank in the first place? Gravity, right? Gravity is pulling it down that distance. So in a way, voltage is what's trying to push it through the the pipe. And maybe you've heard this term before, resistance in ohms. My understanding is you guys were supposed to have learned about this stuff in grade 9, which granted it's been a while, but maybe you've seen this formula like V times I equals R or something like that. I maybe even have the formula wrong. It was grade 9. Long story short, these three things usually go together. Voltage is like how much it's getting pushed by. Current is kind of how fast it's going. And resistance is what's slowing it down. So if you have a resistor, the resistor is trying to slow down your current. So, does that make sense so far? Okay, that initial terminology aside, that's kind of like the physics overlap. Now I want to give you a bit of a history lesson on batteries as well. Probably the first people that we know of who were experimenting with electricity, you probably even heard this story. Like I mentioned Ben Franklin before. Have you guys heard the famous kind of story where he goes out with the kite and the kite gets struck by lightning kind of thing? I think there was a key involved. I don't know the full story. It's probably a legend anyways. But have you guys heard that sort of rumor before? Scientists back in Benjamin Franklin's day, do I have a date on here? I don't. I want to think it was in the 1750-ish range. I should have wrote it down. They were basically experimenting with charges, and they were able to figure out how to store static electrical charges. And you guys probably know a little bit about static electrical charges. Anybody ever had socks on some carpet? Like you rubbed your socks on the carpet, and you go up to your friend and go and shock them? You guys know what I'm talking about there? Or I get this when I'm in my car and I go out and I get gas, and I've been sitting in the car for a while and I open the car door, I get a little bit of a shock. Anybody ever have that before? I don't know. Depends on how well grounded your car is, I guess. Mine does it. So. Anybody ever rub a balloon to their head and then stick it to the wall? Right. Those are all ways where you're kind of accumulating a static charge. The reason I'm using the word static is because it's not continuously flowing in a circuit like our light bulbs are or your calculator is, where the circuit is constantly running. Does that make sense? So these guys I'm going to talk about here, they were able to create a certain form of battery, and I'm not sure battery is probably the right word compared to what you're thinking here, because these things did not emit continuous charge. They were basically able to charge them up once, and then as soon as they ran out of charge, they were dead again, and they weren't really able to run a circuit. They didn't know that stuff. So the concept was called a Leyden jar, and they were actually named after the University of Leiden. Leyden, I don't know if I'm saying it right. And it looks something like this, where they'd kind of have some foil, some glass in between, some foil in between. You'd have some sort of rod at the top here, and you'd try to find a way to charge it up by using, just think of like rubbing your socks on the carpet sort of thing, or rubbing your hair on the balloon. Find a way to charge it using different charging methods, and add some static electricity. Ben Franklin, by the way, I was doing some research. He actually coined the term battery. Here's a picture that I found online. Basically what they were doing here is they were trying to accumulate some charge in this Leyden jar, and they were doing it by like rotating this big mass. And in doing so, it was causing like electrons to kind of just jump a little bit, and they were able to charge this jar right here by causing the electrons to go through this piece of metal. I don't know if that makes sense at all, but basically think of it as like a one-time battery, where it's stored some charge. Maybe you've heard the word capacitor, and moving on. This is really where we need to start from chemistry. In 1800, Volta, which we've actually named the term volts after him, he managed to figure out how to make the first, at least that we know of, first battery that like could be ran on a continuous circuit, and he called them voltaic piles, is the phrase he used. We're going to start doing this in some of our labs, actually, where what he did is he hooked up a jar, and it had two little pieces of metal in it, and then he linked this one to this one, and linked this one to this one, and this one to this one, and I'm guessing he probably linked the last ones to each other as well, and he created himself a circuit. And this is basically your first battery. Your calculator essentially does the same thing. You throw in one battery, and it kind of links up to the next battery, which links up to the next battery, which links up to the next battery, and then it goes and runs your calculator, and then it links back to the first one. Does that make sense? So this is kind of a prehistoric version of it, though. Okay, terminology now. I already mentioned the concept that you're going to have something that needs to lose electrons and something that needs to gain electrons. I'm just using my hands again here. Losing electrons, gaining electrons. From the top again, if this guy loses electrons, loss of electrons is oxidation, means it is the reducing agent. So your electrons always go from your reducing agent to your oxidizing agent. If you can find a way to separate these two things, run electrons through a wire, now you've made yourself a battery. Well, the terminology we now use is, rather than calling these the reducing agent and the oxidizing agent, we call them anode and cathode. You guys ever heard those words before? Basically, it's the two different poles on a battery, the negative and the positive. The anode is negative. It's usually represented by a black cord or wire, and the cathode is the positive one. So if I had to label these as the reducing and oxidizing agent, which one would be which? Which way are the electrons going to go through this wire right here? From black to red, from the anode to the cathode. Why? Electrons should be repelled by other negative things, and electrons should be attracted to positives. So that would mean that the anode is the reducing agent, and the cathode is the oxidizing agent. Does that make sense? I think this slide really, I just need to talk about this last term. You guys can read the rest of it. The term is called a primary cell. A primary, I haven't talked about this yet. By the way, the chemistry word for battery is cell. Sorry, I didn't mention that yet. So we don't actually use the word battery, we use the word cell. A primary cell is a battery that cannot be recharged. You use it once, and once it's been used, you throw it away. The batteries in the back of your calculator, those are primary cells. Does that make sense? A secondary cell is a cell that can actually be recharged. Where do you have secondary cells? Your cell phone, yeah, right? As soon as your cell phone dies, you plug it back in, you recharge it, that makes it a secondary cell. Your car battery is a secondary cell, by the way, which I believe is what this slide here is about. this is what your car battery does. Here, the lead oxide, and sulfuric acid, which, by the way, is one of the equations at the very top of this table in here. Do you guys have those tables nearby? If you have the table, the very, very top one is fluorine. The one right below it is lead 4 oxide and basically sulfuric acid. That's what your battery is made out of in your car. It's pretty much the second strongest oxidizing agent we know of. So here's an oxidizing agent collection here. This lead, by the way, is the reducing agent. The electrons will then cause it to change into something else, but your alternator in your car will actually recharge your battery and cause the reaction to reverse itself and go back to where it started from. That's why we actually use some double-sided arrows to indicate that you can actually make a cell go like this and then reverse it back to where it came from, possibly. So far, so good? Okay. Volta was kind of the main guy that we attribute the name to, so we often call these things voltaic cells in honor of Volta. But I was reading some history the other day, just doing research for this class. There was another guy named Galvani, and he was also working on batteries around the same time. I'm not sure that he got nearly as much credit as Volta did, because we named volts after Volta. But sometimes you might hear these called galvanic cells as well. So either way, a cell is a battery. So we're clear. Okay, so maybe this is kind of the most important section here. What do you need for a cell? Well, you need to have 2 electrodes. That's the term we use. An electrode basically is like a bonding site, where at one of the sites you have to lose some electrons, and at the other site you have to gain electrons. That makes sense? You have to have an oxidizing and a reducing agent. Okay. And the phrase we use is anode and cathode. So cathodes are positive, and it's the site where reduction occurs. What is reduction? Gain of electrons. Positive things want to gain electrons. Does that make sense? The anode is the electrode which oxidation occurs. Well, oxidation is loss of electrons. What sort of things would want to lose electrons? Positives or negatives? Well, positives would want the electrons, right? So negatives are going to lose them. So you're going to have to start trying to memorize the fact that the anode is the negative and the cathode is the positive. Okay. And the electrons always flow from negative to positive. Okay. Here's kind of an important slide then. Our electrodes are usually metals. It works really well in making a battery. If you're trying to make a battery with metals as your electrodes, metals are a great place for electrons to be stored because electrons can move through metals. It's been a while for a couple of you guys, but you might have learned about the terms ionic bonding, covalent bonding, and there was a third type. Grade 11s, you remember? Ionic bonding, covalent bonding, metallic bonding. Do you guys remember that term? Do you guys remember this? It's been a year and a half since we talked about this. Metallic bonding basically means that metals, like say copper, nickel, zinc, all of these metals right here, they have delocalized electrons. You have a whole bunch of positives, and all of these positives are held together by a glue in which the electrons can kind of flow wherever the heck they want through the metals. And that's why metals can conduct electricity so well. You guys remember that term at all? It's been a while. Anyways, long story short here, metals are great things for electrons because electrons can flow through metals quite easily. Does that make sense? And these half reactions can take place on the surface of the metals. Okay. It is, however, possible that sometimes the reaction you're working with is not something that's metal. So then we need to have a metal as the electrode. And so the 2 common things we use are either platinum or carbon. And the reason why is that platinum and carbon, they still can conduct electrons. They still conduct electricity, but they're inert. Do you guys know what the word inert means? Anybody know what inert means? You ready to try?
Not in movement.
Say that again?
Not in movement.
Close. Inert means non-reactive. Non is right, but Inert means non-reactive. Okay. If you were to look on this table right here for platinum and carbon, they're not on there. Does that make sense? And so that's actually why we use them, because they're not going to accidentally be part of the reaction. So we can use them as an electrode, basically as a site for electrons to flow through. Let's go to the picture here. I think it's time to start diagramming our first cell. This is kind of Volta's original cell. And I can actually, we're going to make one of these in one of our labs, actually, where we're going to use some chemicals and we're going to make a battery. 1 year with a group of kids, we actually ran a calculator off of a battery. Like, we took the batteries out of the back of the calculator and we ran the calculator off of basically 2 beakers, 2 pieces of metal, and a wire. Yeah, that's pretty cool, actually. I wasn't sure it was going to work, and then it actually did. Like, I mean, I knew it was supposed to. I wasn't sure it would. So let me walk you through what should happen here. Okay. This guy right here and this guy right here, these are called the electrodes. They're basically the bonding sites. One of these things is going to have to be the reducing agent, and one of them is going to have to be the oxidizing agent. I don't know necessarily which one's which, but does that make sense? You have to have one for each. What is an oxidizing agent? Well, an oxidizing agent is something that is reduced. Reduction is the gain of electrons. So this is the bonding site where we're going to have a lot of electrons start showing up over here. Does that make sense? Well, where do the electrons come from? They can't just magically appear. Well, someone else must lose the electrons. Well, that's what happens over here. This guy over here is going to lose electrons. And electrons are going to flow out of this metal, and they're going to travel along this wire from here to here so that the electrons show up over here. Does that make sense? Well, if this guy's going to lose electrons, typically what happens is this metal, I'm just going to write X solid because I don't know which metal it is just yet. But the metal, in losing the electrons, will probably turn itself into an ion and spit out those 2 electrons. And what happens is this particular electrode, it starts to like waste away and corrode. And like this section right here, it's going to like dissolve. We've actually seen this before. If you drop magnesium metal in hydrochloric acid, you can literally watch the magnesium metal just dissolve in front of your eyes. But did it disappear into nothing? It didn't disappear into nothing. It turned from magnesium solid into magnesium ions. Does that make sense? And that's what's going to happen here is this solid chunk of metal is actually going to turn into some ions, and you're going to get a whole bunch of ions in the solution. Does that make sense? We would call this electrode the anode, and on a battery we represent it with a negative symbol because it is losing electrons. Electrons want to leave something that is negative. The electrons then travel through a wire. At some point during their journey, you have them run something, like your light bulb or your calculator or your cell phone. Does that make sense? Like, you interrupt the journey so that the electrons can do their electricity per whatever it is they need to do, right? And turn on your device. Then they keep going, they get gained over here. Do you guys remember the initial definitions of oxidizing and reducing? What was the initial definition of reducing? Like the historical one. Taking something and turning it into a pure metal, yeah. Well, you now have a whole bunch of electrons sitting over here on the surface of this electrode. Well, what's going to happen is there's going to be some ions. I'm going to call them Y2+. There's going to be some ions in this little solution right here. And those electrons are going to be, these ions are going to be attracted to those electrons. Because don't positive ions attract themselves to negative electrons? And what's going to happen is on the surface of this electrode, there's going to be a buildup of solid. Because what's going to happen is Y2+ is going to pick up some electrons and turn into Y solid and therefore be reduced. This is the positive electrode, and we call it the cathode. Does that make sense? Okay, now, in order for your battery to run, Over time, what's going to happen is your battery is going to become very polarized. So imagine over time what happens is this piece of metal starts dissolving. And in the course of dissolving, it spits out a bunch of positive ions into this beaker. So this beaker here becomes very positive. This actually becomes counterintuitive to how the battery works. Because aren't the electrons supposed to leave? But if there's a bunch of positives in this beaker, why would the electrons leave? That makes sense? It actually is a problem, right? As the electrons leave and run through your circuit over to here, you have a whole bunch of positives sitting inside the beaker. Well, the electrons that are currently in this piece of metal that are about to leave through the top wire, that's one option. Or the other option is, why don't you just stay? There's a whole bunch of positives right here. Don't negatives want to be by positives? That actually becomes an issue. So all batteries have to have either a salt bridge or some sort of porous electrolytic solution. And if you've ever cut open a battery before, anybody ever seen that white kind of oozy stuff, the kind of maybe even green stuff that's inside a regular battery? There's kind of a paste on the inside of it, and it's what helps preventing a battery from becoming polarized. What we typically do is inside this little U-shaped thing, which we call a salt bridge, we put, usually in our lab, we're going to put potassium nitrate. It doesn't have to be potassium nitrate, but that's usually what we do. And the salt bridge helps preventing polarization of the cell because as this beaker becomes very positive, through the process of diffusion, so kind of a biology overlap here, you guys know how diffusion works? Through the process of diffusion, the negative NO3 ions will migrate themselves over this direction right here, and these negatives will counterbalance all the positives that are getting spit into the beaker, therefore preventing this beaker from becoming too positive. So that the electrons can actually take the back door path around there. Does that make sense? Conversely, over here you have a beaker where a whole bunch of positive cations have now become attracted and turned into solid metal on this electrode right here. Well, if all of the positives leave this beaker would actually become very negative because all of the positives are leaving. That becomes a problem because why would electrons want to go through a circuit and show up somewhere where there's a bunch of negatives? Does that make sense? Sometimes I use an analogy of maybe going to a party. Hopefully this isn't too offensive here, but hopefully this makes sense. I'm going to go with it. There's a party Friday night, and a couple of guys are texting, and they say, there's a party over here, and there's 20 girls at this party, and there's only 3 guys at the party. So the guys are like, oh, we should go to that party. There's lots of girls there. Does that make sense? But what happens if you showed up at that party, and all of a sudden, actually, there weren't 20 girls there anymore. There were 17 guys instead. Does that make sense? That's kind of the analogy I have going on here, if that makes any sense at all, where here's a whole bunch of electrons. The electrons want to go over here because they thought that there were some positives that they could be attracted to. But the problem is, as the positives were used up, all it left was negatives. Why would the electrons then want to go to somewhere where there's a bunch more negatives? Does that analogy make sense? So this is where the salt bridge comes in again. See how there was potassium and nitrate? The nitrates go to this side over here. The potassiums would use diffusion, and they would migrate over this way. And so these potassiums right here would find a way to keep these negative charges occupied so that the electrons could actually keep flowing and keep the circuit running. That's a battery. There's a lot there, eh? So, does that make sense, though, for the first run through? Okay, cool. So let me actually just go back to the slide I skipped here. In order for this to work, you're going to need to have some electrolytes. These electrolytes are the solutions right here. You need to have this solution right here of electrolyte. Anybody hungry?
Anyone gonna eat? We have cheese strings. Yes! I'm like, people eating. It means they're healthy. Yeah, we eat cheese strings instead.
Processed cheese probably too. Thanks, guys.
No problem.
Okay, so that's one thing. You need to have some electrolytic solutions because you have to maintain the flow of ions. You can't just have the electrons flow because otherwise the cell becomes polarized. Does that concept make sense? as the electrons flow, it's actually counterintuitive. Okay? You need to have porous boundaries. So typically we either use a salt bridge. There's another possibility. It's called a porous cup, and I'll show you the example of a porous cup in a bit. Yeah, and this is what I was just talking about. You try to prevent polarization. So there's a battery. This is the notation we might use to describe a battery. This notation works like this. The first thing right here is the anode. What happens at the anode? Well, anodes lose electrons. Okay. So copper is going to lose electrons. This right here is the solution in the beaker right there. Because you have to have a spot for the copper ions to get lost to, if that makes sense. This guy right here is the electrolyte in this beaker right here. And then this guy right here is the cathode, which is the thing that's going to gain electrons. It's a bit of a misnomer, actually. The silver solid is actually not what's going to gain the electrons, because the silver solid already has electrons. It's actually this silver right here, the Ag+. It's going to gain the electrons and turn into solid silver. And what happens is you get a bit of a buildup on this electrode. You see how this electrode right here, you can kind of see there's a bit of a buildup on one side of it? And this electrode right here is kind of wasting away and dissolving. That's because this one right here is losing its electrons. And in doing so, the electrons are going through the wire around like this. But in losing its electrons, solid metal is turning into ions, positive ions. Does that work? Okay, I've been holding off on this concept for a long time. It's called the cell potential. If you're then wondering, well, how strong is your battery? There's some numbers on your data table that tell you how strong your battery is. When you guys use batteries, you maybe have seen like 1.5 volt batteries, 9 volt batteries, you know what I mean? Well, that's where these numbers come from. This list, in addition to be a ranking system of oxidizing agents and reducing agents, it can also be used to tell you how much voltage a battery has. And it's really simple. All you have to do is find the number for the cathode reaction, the number for the anode reaction, and subtract them. That's it. We've actually arbitrarily put the number 0 right in the middle of the table so that half of these things are positive and half of them are negative. And we just kind of arbitrarily chose hydrogen to be in the middle at 0. But it's kind of like a burette. You guys know how when you're using the burette yesterday, if you first measured a volume of 3.75 milliliters, is that actually a volume that means anything? And let's say, well, no, because you take the 3.75 you start with and the 12.8 you finish with, and you subtract those two numbers. That's kind of how this table works. On an individual level, these numbers here mean nothing. But when you combine them with the second number and subtract them, that's where the voltage comes from. So we just have to randomly choose which one gets to be 0. So it's hydrogen. So, for example, if you had a battery made up of copper and of hydrogen, if that's what your battery was made up of, its voltage would be 0.34. Because copper is at 0.34, hydrogen's down there at 0, so 0.34 minus 0 means you've got 0.34. Does that make sense? If there is a positive number, it just means that it's stronger up on the table. And if it's a negative number, it just means it's lower on the table. Here I've got a picture of a battery that would be hydrogen with aluminum. If you made a hydrogen/aluminum battery, you would take 0, and then you would minus negative 1.66. Well, what happens when you minus a negative? You just add, right? So an aluminum hydrogen battery would have 1.66 volts. If you know much about batteries, I think I've chatted with a few of you about this before, a lot of batteries are made with lithium. Why? Well, look on the table. Lithium is about as far down as you can get, which means that it's going to provide one of the bigger voltages you can have. So a lot of batteries are made of lithium and cadmium, lithium and nickel and cadmium. Those are some of the typical batteries. So that actually kind of helps explain why, because they're so low down there on the table. Okay. Here's a picture then of a cell, and this is kind of a rehashing of what I just did with you guys earlier. So maybe let me try a second time explaining what's happening in this battery, and then maybe we'll take a break. So let me walk you through all the different steps of what's occurring in the battery. Okay. So first things first, I'm going to start over here. It happens to be that this one could be a better one to start with. This one over here, do you see how it's kind of wasting away down to a bit of a point? This guy right here is losing electrons. Because he's losing electrons, he's being oxidized, which means he's the reducing agent. And I think I know that because solid copper is on my data table right here, and it is in the reducing agent side of the table. Does that make sense? The electrons are then going to be lost, and they're going to go through the wire. And I'll pick up the electrons in a bit, but let's talk about what's occurring here. Solid copper is turning into 2+ version of the ion and spitting out the 2 electrons. And so what's happening here is this beaker is now becoming very positive. That's a problem. Because if you're an electron wanting to leave, but there's a whole bunch of positives there, why would you leave? If you like that whole example of like a party sort of thing, if these are a bunch of, I don't know, girls leaving a party, but there just so happens there's a bunch of guys at the party, why would you leave? I don't know. Hopefully that makes sense. Hopefully it's not too offensive or anything. So that causes a problem. Right? So in doing so, you have to have the salt bridge right here. Potassium nitrate works, sodium nitrate works. Diffusion is going to cause these nitrates to come through this salt bridge right here, and the negatives will kind of counterbalance all of those positives so that the electrons actually have a reason to leave still. Does that work? So over here, the electrons are now being built up on the surface of this metal. And this metal right here now has a ton of electrons. Well, in the beaker right here, you have Ag+. You put some silver plus ions in the beaker. Well, those silver plus ions are now going to become attracted to those negative electrons, and you're going to get a buildup of solid silver right here, as the silver ions add electrons and make up solid silver. But we have a problem. As soon as you remove these positive ions from the solution, this solution is going to start to become very negative. Well, this is great. That's where the sodium comes in. The sodiums will now come in and kind of use this sodium, and those negatives can kind of bond-ish kind of together to prevent the cell from becoming too polarized, because otherwise all these negatives right here would prevent these negatives from wanting to show up. Does that make sense? That's actually the definition of anode and cathode, by the way. The reason we call it an anode is that anions migrate towards it. The anions would be this this nitrate is a negative. The negatives have to migrate this way. Hence the term, this is called an anode, because anions move that way. This one right here is called the cathode because cations migrate towards it. Remember, cats have positives. These positive sodiums are making their way over here. So that's actually where the names came from for anions and cations. Or sorry, anodes and cathodes. Okay, one last thing then. How much voltage would this cell have? So we have a battery that seems to be running. How much voltage would it have? Well, we need to find the two equations. The way it works is to find the, this is the notation we use by the E cell. So basically, this is the voltage, if you're looking for that. You find the cathode number. So the cathode is silver. Silver is positive 0.80. And you subtract the anode number, which is copper. Copper is positive 0.34. So this is a battery that should produce 0.46 volts. But it's a start. In order to make batteries that are stronger, they then make multiple cells and they put them in series. Do you know the term series versus parallel? Okay. Maybe this diagram right here kind of can demonstrate it. Then we'll take a break here. Actually, that one will work too. This will work here. Here's a cell that's 0.46. Here's a cell that's 0.46. Here's a cell that's 0.46. Put them all together. 5 cells at 0.46 now gives you like a 2-volt battery. Does that make sense? Cool. How did I do so far? Cool. Okay, let's take a break. Okay, so find this question here. This is what they would give you on a diploma. Most of the stuff we do with this battery cell concept is going to look something like this. They're going to give you a picture of a cell, and it's going to be your job to interpret what is happening. So sometimes it takes quite a while because there's a lot of labeling that I like to do. First, I'll label things like, well, who's oxidizing, who's reducing? Who's the oxidizing agent? Who's the reducing agent? Who's the anode? Who's the cathode? Which way are the electrons going? Does that make sense? Do you guys have this picture there? Oh, it's just because they're only 4 per page. Okay, so let's show you how to solve a question like this. Hopefully now you can look at this and you can say, okay, this looks roughly like what a battery should look like. Granted, it's not actually in 2 separate beakers, but ignoring that sort of design, does that kind of look like a generic battery now? So our goal is let's interpret it. The first thing you need to do then is you got to figure out a beaker of stuff kind of question. What do we have? So I got to find a table somewhere here. Oh my goodness, why do I not have one nearby? Okay. What sort of stuff was in that beaker? What were the 2 electrodes made out of? Copper and cadmium? Okay, so I'm going to need to circle cadmium down here and copper up here. What were the 2 electrolytes made of? I'm thinking it was cadmium and nitrate and copper and nitrate. Is that correct? Okay, so that means I should have copper 2+. I should have cadmium 2+. And I'll circle the nitrate right here as well. There's 2 more things you need to circle as well. These were aqueous solutions. So we have to consider the fact that water is involved. So that's where I start. Is this thing capable of running as a battery? Is there a spontaneous reaction occurring somewhere? From the nitrate? Not unless it's acidified. So, but hopefully you'd agree that this guy to this guy, there's a reaction that occurs. So I'm going to write out that Cu2+ is going to need to gain 2 electrons and turn into solid copper, while simultaneously cadmium solid is going to spit out 2 electrons and turn into cadmium 2+. That's my equation that's taking place, the 2 of them simultaneously. This top one here is the gain of electrons, and this guy right here is the loss of electrons. So I can now start to label my battery here. Copper is gaining, cadmium is losing. Copper is gaining. So copper is gaining electrons and being reduced. Cadmium is losing electrons and being oxidized. Does that make sense so far? So that got me started. Now, granted, I'm going to label way more on the cell than it asks for. And the only reason I'm going to do that today is because sometimes they'll ask you for anode, cathode, and movement, but they could ask you for so many other things as well. So I'm just going to label the crap out of the cell, everything I can think of. So if this guy is being oxidized, it is then the reducing agent. That makes sense? And if this guy is being reduced, it is the oxidizing agent. If this guy is gaining electrons, electrons are attracted towards positive things. And the positive is the cathode. If this guy is losing electrons, why is it losing electrons? Well, electrons want to leave other electrons, negatives, and the negative is the anode. While I'm at it, that's actually the definition of which way the ions migrate. The anions are going to need to move towards the anode, and any cations are going to need to move towards the cathode. In this wire up here, the electrons go away from the negatives and towards the positives. I also like to do 2 more things here. I like just to make sure that I know that what's happening here is the gain of electrons is going to cause this particular electrode to have a bit of solid buildup on it. because it is gaining electrons, therefore turning itself into a more metal. And this electrode right here, it's harder to draw it like this, but this electrode right here is going to kind of waste away a little bit and is going to cause some ions to drop off of it as it like dissolves, I guess. This one is going to dissolve, and this one is going to, I don't know, build up. Does that make sense? This is what should happen in our battery. Now let's answer the question. Where's the anode? 4. Cathode? 3. Which way are the anions moving? Anions move towards the anode. Let's just talk about why one more time. I know I've been repetitive on this. What should be happening here is this anode is losing the electrons. In losing the electrons, it's spitting out a bunch of positives. Well, why would electrons want to leave the positives that are there? Well, negative anions are going to have to move this way to kind of counterbalance those positives, so the electrons would want to leave. So the anions are moving this way, which is number 5. And lastly, the electrons always go from anode to cathode, from the negative to the positive. So they're going according to number 1. That makes sense? This is a classic question. Like, they usually ask more than one of these on a test, where they're going to give you a picture, look at the picture, interpret what's happening. I like to just label everything, and then answer the 4 little things they put on that. It's like a matching question, right? Does that make sense? Could you guys do that? Maybe not right this minute, but you kind of possess those skills with a bit of practice. Okay, what did I skip here? I skipped the practice. Okay, where did I finish? I finished here. So what was I going for here? Oh, okay. Sometimes we need to do a chemical reaction, and the stuff that's reacting does not involve a solid. Let me show you an example here. When we did our lab yesterday, we were using, say, permanganate. Look at this permanganate. There's an aqueous. There's an aqueous. On the other side of it, there's aqueouses and liquids. Where are the electrons going to sit if everything's aqueous? Because electrons need to sit on the surface of a metal. Does that make sense? And there's quite a few reactions here that don't involve metals. Like, for example, the classic middle one right here, hydrogen, aqueous to gas. Electrons can't just, like, sit in the middle of gas. Does that make sense? Well, actually, they can, but not for our purposes. Okay, so we might need to use the inert electrodes, and one of them is carbon. Another one is platinum, by the way. Those are the 2 inert electrodes. So here's an example of a cell, like I kind of showed you, where it looks like what's happening here is copper and copper 2+ are going to react. And over here, this carbon is actually not really what's occurring. It's going to be the dichromate and the hydrogens. They're doing something, but we can't make an electrode out of aqueous stuff. So that's why we have to use carbon. Does that work? Okay, let's try some more examples here. No, not yet. Okay, sometimes rather than having 2 beakers side by side, someone really smart came up with this idea of taking one beaker and putting it inside another beaker. That's basically what a porous cup does. Is rather than having this beaker sitting over here on the outside, you put a beaker inside a beaker. So this is a beaker, this is a porous cup. Okay. Porous meaning that it's semi-permeable. You guys know the word semi-permeable? Ions should be able to flow through this. Solid matter and water, too big. But if it's a dissolved ion, it has that ability. So rather than having these 2 beakers side by side, put them inside each other. It's helpful because it saves on space. Right? And I mean, isn't that a key thing on batteries nowadays? You want them to be small. So what ends up happening is you put one electrode inside the porous cup, you put another electrode outside the porous cup but still inside the other beaker, and ions flow through this barrier instead. Okay, let's try the examples. We need some practice. Actually, this is just an exemplar, just showing you a cell. Let's do this one. Diagram and label the following cell. So what this notation means is it's going to tell you first what is the anode. Then it's going to tell you what is in the solution next to it, which is called an electrolyte. The double bar kind of indicates that you're kind of changing over to the other half of the solid. Then this is the stuff in the other beaker, and then this is the cathode. So I'm going to start labeling stuff here. This is made out of carbon. That should actually instinctively set off warning bells. Why would something be made out of carbon? Because it's not, like, there's nothing solid happening. We need an inert electrode. In this beaker, we're going to have some iron 2 pluses and some iron 3 pluses. On the other side, we've also got carbon solid. Why? Well, chances are we don't have any solid materials in our reactions. But we do have some Cr2O7s and some H pluses. So far, so good. Okay, this is a beaker of stuff. Technically, it's 2 beakers of stuff, but let's go circle a bunch of stuff on our data table wherever we have one. Apparently, I don't have one. There we go. Oh, that's not an eraser. Okay, I don't have the slide next to me, so help me out. We had iron 2 and iron 3, correct? Okay, so then iron 2 pluses right here, iron 3 pluses right here, iron 2 pluses right here. We had carbon, but that's not on the table on purpose. And then we had dichromate and hydrogen. So, I mean, technically hydrogen by itself is right here, but dichromate and hydrogen is right there. I should also count for the fact that there's water involved, because once in a blue moon, water actually is a reactant. Can this thing operate as a battery? Is there a spontaneous reaction taking place? Okay, so the first thing to do, write out what the equations are. One of the equations is going to be that your Cr2O7 plus the 14 hydrogens is going to need 6 electrons, and it's going to turn into 2 chromium 3 pluses and 7 waters. Is that the oxidizing reaction or the reducing reaction? That's the reducing reaction. How do I know that? Because it's gaining the electrons, yeah. So this is the gain of electrons. Okay, so I'm just going to hop over here real quick. Too far. Over here, I need something to gain electrons. The dichromate is going to gain electrons. Does that make sense? Once I get that started, really the rest just should logically fall into place. If this guy right here is gaining electrons, wouldn't this one over here have to lose electrons? So the way it's going to work. The equation for this one, by the way, is going to be Fe2 plus going to Fe3 plus and spitting out 1 electron. That actually kind of explains why it told me that there was Fe2 plus and Fe3 plus. Because what's going to occur here is Fe2 plus is going to touch this metal. It's going to pick up, no, not pick up, it's going to lose an electron. The electron will then go through the wire. And after it loses the electron, the Fe2 plus will turn into an Fe3 plus. So this beaker should be full of Fe2 pluses, and they're actually changing into Fe3 pluses. In doing so, losing electrons this way around the wire. A whole bunch of electrons are getting picked up over here, and then that dichromate reaction can take place, where it turns into, what did it turn into? Chromium 3 plus and water. Okay, what else can I label? If this thing gains electrons, it is the oxidizing agent. If this thing loses electrons, it's the reducing agent. This is the positive, because electrons flow towards positive things. Gaining electrons, losing electrons. If you're losing electrons, why are you losing? Because you're negative. Electrons flow away from negative things. This means this is the anode. This means this is the cathode. In terms of my salt bridge of ion flow to prevent polarization, positives are going to have to migrate this way, and negatives are going to have to migrate this way. Okay, that more or less kind of labels myself for me. Does that make sense? Okay, let me do one more and then I'll skip the third one. I think you get the point. I want to keep moving here. So let's just do one more. Scandium and copper. Find scandium. Yeah, I don't think it's on there, is it? Okay. Well, if scandium's not on there, then does that mean we can't do it? Well, the good news is that this notation actually kind of gives away what's occurring. Okay. I know this one's the anode and this one's the cathode because of the order it's written in. So I actually already know some of this information. I'm going to say that this guy right here is scandium, and that this one right here is copper. And here there's some scandium 3+ ions, and here there's some copper 2+ ions. So I don't even need to look at the table actually to kind of get this started. If copper is supposed to be the cathode, what happens at cathodes? Good. By the way, there was an acronym on a slide there where it was like what was it? Red Cat. Yeah. Somewhere way back here, I skipped it. Red Cat and anox. That can kind of help you memorize which one is which. That one's not bad. When I was in school, I learned it as Leoa and Gurk. So like, you know how I've taught you Leo says Gur? When I was taught this, it was Leoa says Gurk. So if you have something that is the cathode is gaining electrons, and the anode is losing electrons. There. I labeled a whole bunch of stuff. Anode, cathode, negative, positive. The electrons, therefore, are flowing this way around the circuit. Okay, so what should be happening in these beakers? Well, if this guy is losing electrons, what should be happening is the scandium solid should be turning into scandium 3+ and spitting out 3 electrons. So is this electrode getting bigger or smaller? Right, smaller. Because what's happening is it's wasting away, it's decaying or dissolving, and it's turning into those scandium 3+. Which actually helps to explain why we need to have negatives on this side of the porous tube, because otherwise this beaker becomes too positive. So the negatives have to come counteract it. I guess that would mean that this is going to have to be the positive one here, because what's happening here is these coppers are getting attracted to all these electrons on the side of this piece of metal, and it's causing a buildup of solid copper. Does that make sense? One thing I forgot to do on the last example, I didn't calculate the voltage. Okay, but the voltage is easy to calculate. If you have the numbers in your data booklet, just find the 2 numbers and subtract them. Is that easy enough to just tell you how to do? You can handle that? Cool. Questions? You guys okay to keep going? Okay, one last topic then. Skip ahead to, okay, here's a summary of voltaic cells. You guys can just read this stuff later. Okay, there's actually another type of cell that was discovered after the voltaic cells. So voltaic cells are a battery which produces electricity. Someone really clever once figured out that if you added electricity, you can actually force reactions to happen. And that's actually a different type of cell. It's called an electrolytic cell. Has anyone here ever, I mean, maybe I've mentioned it before, but anyone ever heard of the term electrolysis of water? Basically what we do is we take regular old-fashioned water, and water should not react with itself. If you look for water on the data table right here, water's down here and water's up here. It should have no reason to react with itself. But if we add electricity, we can actually cause the internal intramolecular bonds to break, and you can cause water to turn into hydrogen and oxygen gas. And basically the concept is add electricity. Rather than receive electricity like a voltaic cell, an electrolytic cell means input energy. Here's a picture of basically the electrolysis of water. What you do is you hook up a battery to it, and it actually forces a non-spontaneous reaction to occur. Does that make sense? So I've got some slides here talking about just the definitions here. A generic term you might come across then is the term electrochemical cell. Electrochemical cell basically means any sort of battery type device, okay? But it could be voltaic, in which you use chemicals to make electricity, or it could be electrolytic, in which you take electricity and make chemicals. Your cell phones are both. Because when you're running your cell phone, it's a voltaic cell. It causes the chemicals in the battery to give you electricity. When you recharge it, you add electricity to it, and you cause it to go back to where it started from. Hence the recharging. Does that make sense? So the generic term for the battery in your cell phone would actually be an electrolytic cell, because it's both voltaic and electrolytic. Sorry. The generic term for the battery in your cell phone would be an electrochemical cell. Does that make sense? I like this concept here, an electron pump. In the electrolytic cells, you're forcing the electrons to go against their will. Normally electrons want to go from anode to cathode. But when you plug your cell phone in, the electricity in the wall forces them to go back from cathode back to anode. Basically, it reverses it. Does that make sense? So here's a summary. Voltaic cells take chemicals, make electricity. They occur spontaneously, and your cathode has to be above your anode in the table here. Basically, you need to go from here down to there. The electrolytic cell uses an outside power source, and it forces a reaction to proceed against its will. By the way, you don't need a salt bridge on these, because you're not worried about a cell becoming polarized over time. So you actually use electricity to produce a chemical change. Or if you want to write this in here, this is when you recharge your battery. There's a table that basically talks about kind of the things that happen. Really, the only difference is, there's only two. Nope. There's three, but one of them is not on the slide here. A voltaic cell is spontaneous. An electrolytic cell is not, unless you add electricity. You know, when we have a voltage, a voltaic cell, we say that it has a positive voltage. An electrolytic cell, we actually say that it has a negative voltage. So when you're recharging your phone, you're actually using a negative voltage in a way. Okay. There is one more change as well. We flip the sides, the signs on the battery. You know how cathode was positive and anode was negative? We flip those. So on an electrolytic cell, we actually make the negative be the cathode and the positive be the anode. Wow. I have a slide about that. Let me see if I can find it here. So the labeling of anode and cathode is reversed by convention, and it's mostly safety reasons, so that color coding can be used to recharge your batteries. So like attach positive to positive, attach negative to negative. That makes sense. So according to technological definitions used by electricians, current is supposed to flow from high potential to low potential, therefore from positive to negative. But we're actually making it go from anode to cathode, so therefore we need to make the anode positive now and the cathode negative for this to work. So, let me show you a picture then. Here is a piece of silver and a spoon. That should not react. We're going to force it to react by using a battery. Has anybody ever heard the term electroplating? Okay. Electroplating basically means that you force the surface of a metal on top of another metal. For example, you could gold plate something. If I wanted to gold plate my spoon, the inside of the spoon is a cheap metal, like, I don't know, lead. But the outer surface of it is gold. And it looks like it's all gold because only the outside surface of it is coated with gold, but the inside is actually a different metal. Does that make sense? Our coins are usually made out of this. There's a famous story about how Archimedes was asked to try to solve a problem for a king because the king thought that he was being ripped off because he was getting a crown that looked like gold, but he thought that perhaps on the inside was actually a cheaper metal. And so he asked Archimedes to try to find a way to figure out whether it was pure gold without breaking his crown, because if he opened up his crown, then his crown is broken. Does that make sense? And maybe you've heard the story, Archimedes was in the bathtub, saw water splash over the side, and then he ran down the street naked. You ever hear that story? Anyways. I got sidetracked. Here's the concept here. What we're going to do is we're going to take silver, and we're going to force silver to lose its electrons. Silver doesn't want to lose its electrons. We're going to force it to. This battery is going to pull the electrons out of the silver. And so silver, solid, is going to turn into silver aqueous. It doesn't want to, but we're going to make it. The electrons are then going to run through the battery. The battery is like a pump. It forces the electrons onto the surface of the spoon. Now this is where it's really clever. This silver solid spit out some aqueous silver. And so now in this beaker, there's some aqueous silver. But look, over here, there's a bunch of electrons now. What would positives want to do with electrons? Yeah. And so what ends up happening is a cheap metal spoon made out of, I don't know, whatever it is, zinc, well, is now coated on the surface with silver. And it plates it. Does that make sense? And we're forcing the electrons to go through the wire using a battery. So what ends up happening here, though, you know how anodes are normally negative and cathodes are normally positive? The convention is flipped. To make this work, you have to hook up your anode to the positive side of the battery, and you have to hook up your cathode to the negative side of the battery. That's all. So that's like the only flip. Flip the positives and negatives. It's not a spontaneous reaction. And so the voltage, if we talk about voltage, we actually use a negative voltage to describe that we need to overcome that voltage for it to occur. Here's a picture, maybe describing the same concept. The electrons are going to go through this wire here. They're going to run from the anode to the cathode, but it's reversed this time around. Anode is now positive, cathode is now negative. We're ripping the electrons out of this metal. The metal does not want to lose the electrons. Tough. We're ripping them out anyways. These guys right here come off the surface of the metal. The electrons come over here. That's these little red balls. And they get coated on the other side. So the cathode gets coated. Okay. Anode and cathode still gain and lose electrons. The anode is still the thing that lost the electrons. The cathode is still the thing that gained electrons. We just flipped the signs, that's all. Okay. Oh, I made it. Okay, one last example. So we're going to set up an electrolytic cell. It's going to have a power supply, and a bit of a thought here. If you ever get a diploma question and they show you a battery attached to it, it means it's electrolytic. Does that make sense? That diploma example that I showed you guys a while back here, whatever it was, like 80 slides ago. Do you see how right here they just put a little V right there? That's a good indicator this is a voltaic cell. If they were to put a battery right here, that's a good indicator that it's an electrolytic cell. Does that make sense? Anyways, back to our last example here. We are going to set up an electrolytic cell with a power supply, 2 nickel electrodes, and an aqueous solution of cadmium nitrate and zinc nitrate. We're going to try to draw and predict how the cell is going to work. So, the big difference between electrolytic cells and voltaic cells, we don't actually need them in different beakers. We actually want them in the same beaker. So I'm just going to set up one beaker here, and I'm going to put an electrode in each of them. And I'm going to hook it up with a battery. Do you guys remember that initial battery notation I showed you where there's 2 different lines of different sizes next to each other? Yeah, so I'm going to go with a little line and a big line. Which one was which again? I believe this one's the negative and that's the positive.
The big one is the positive.
The big one's the positive? I'm going to go back to my first slide. I haven't used this notation since physics. It's been a while. Oh, too far. Which one was it? The little one's negative, the big one's positive. Okay. Okay, little one's negative. Okay, so I screwed it up, didn't I? Little one's negative, big one's positive. Good so far? Okay. This means that this one right here, positive is normally the cathode. Now it's the anode. Negative, normally negative is associated with anode. Now it's the cathode. Now, that's the only change. Anode still loses electrons. Cathode still gains electrons. So if you like my Lioa and Girk thing here, that doesn't change. Okay. What we're doing though is we're forcing the electrons to go through the battery that direction. Does that work? The last things I've got to do, actually one more thing before I get to my table. It says these guys are nickel, so I'm just going to write nickel on these ones right here. I want to now circle stuff on my big data table, if I can find one nearby. Shoot, I gotta go all the way back. Okay, help me out. What else do we have? We have nickel solid, it said, right? So nickel solid's right here. What else do we have? Zinc nitrate? Okay, so nitrate will be right here. Zinc as an ion will be down here. Cadmium as an ion will be right here. Okay. Is that it tells us about? Yeah, okay, so it's aqueous. Boy, I poorly chose this example, didn't I? Okay. Actually, no, it wasn't that bad. I can still make my point that I want to. Do we have a spontaneous reaction occurring here? No. If it was acidified, I would, because then I'd have the H plus required to make this occur. So will this reaction take place? No, it will not. However, we can force a reaction to take place. The first reaction to take place will be this one right here. If I were to add whatever the difference in voltage is between right here, if I were to add that amount of voltage, I could force this nickel to spit out nickel ions and cause cadmium to become cadmium solid. Does that make sense? If I added enough voltage. If I added a little bit more voltage, I could cause zinc to get plated. And if I added even more voltage, I could actually cause water to turn into hydrogen gas. So the trick to an electrolytic cell is you only add just enough voltage. Sometimes kids think it's not working. Bigger is better, add more voltage. Sometimes what that does is it causes other reactions to take place. So the first reaction that's going to take place is we're going to make the nickel solid go backwards into nickel 2+, and we're going to make cadmium turn into cadmium solid. I just need to find out how much voltage is required here. That's a -40, right? And a -26?
0.14.
Okay, so I need -0.14. Basically, I'm lacking 0.14 volts. If I take a battery and add just a little bit of voltage, I should be able to make this occur. So, I'll go back to my slide here and we'll diagram it, and then we can be done for the day. By the way, thanks guys for bearing with me for an hour and a half. All right, so what did I say was going to happen again? I said that cadmium, is that right? Cadmium was going to turn into cadmium solid, and I said that nickel was going to turn into nickel ions. Is that what I had concluded again? Don't have to go back to that slide. I don't remember anymore. Nickel was supposed to go to nickel 2+, right? Yeah. Was it cadmium that was going to cadmium solid? Okay. Okay, so let's label that. If cadmium is going to go to cadmium solid, it needs to gain the electrons. So I should expect gaining of electrons right here, meaning that on this electrode right here, I would expect to see a buildup of solid cadmium on the nickel electrode. Basically, we're electroplating cadmium on top of nickel. At the other electrode, this solid nickel is going to waste away and turn into nickel 2+ ions. Now, it wouldn't normally do that, but we're going to rip the electrons out of the nickel, force them around the other side, and if I were to add that many volts, I could cause this reaction to take place. If I up the voltage, and this is where sometimes you plate more than one metal at once, if I up the voltage, I could plate both cadmium and zinc at the same time. Does that make sense? If I had enough voltage. So I could cause my zinc 2+ to also plate right here. Okay, summary of the day then. Like I said, sorry it was so long. What do you guys think? Was this an effective lesson even though it was an hour and a half? So this is really 3 lessons in one. First lesson is I need you to know basically about how a battery operates. The battery operates by removing the 2 oxidizing reducing agents running a wire. I need you to be able to look at a picture of a cell and interpret what the heck is happening. So basically, if I give you a picture like that diploma question, you should be able to tell me which way the electrons are going, which one's the anode, which one's the cathode, which one's the reducing agent, which one's the oxidizing agent. Okay. Second thing you need to be able to do is figure out how much voltage a battery either gives off or requires. And that kind of throws into the third topic, which is voltaic cells produce electricity, but you can actually recharge a battery using an electrolytic cell by using electricity, like say from the socket, and recharge your battery. One of the best things you can do with that is actually this electroplating concept, where you force the electrons out of one metal, throw them through the wire to the other metal, and then cause that metal over here to suck in the ions, plating the outside of it, so you get like, I don't know, chromium plated something. Trucks, a lot of times, will chrome plate their, the rims and stuff, right? Does that make sense? They're not pure chromium, they just plate just the outside of it so it looks shiny. Sound good? Okay, tomorrow's a work day, but I'm going to try to do some demos. Okay, I'm going to grab some chemicals and I'm going to show you guys how I can make a battery using some cells. So, other than that, we're kind of done for Easter. So, tomorrow's kind of a flex day. I hear you guys have an English test too, so you can probably use some time tomorrow to study. Sounds good? Thanks for being patient with me for an hour, guys. Hour and a half, actually.